The Biot-Savart law expresses the relationship between current and the magnetic field produced by the current. The Biot-Savart law is used to calculate the magnetic induction at a point in the magnetic field produced by the current. Now, consider a finite, long conductor XY of any arbitrary shape carrying a current I. Let P be a point in the magnetic field of the current-carrying conductor. To determine the magnetic induction B at point P, due to the current carrying, let us assume the conductor is divided into a number of infinitesimally small elements, each of length dl. First, let us calculate the magnetic induction dB at point P, due to one such element of the current-carrying conductor. Then, to obtain the magnetic induction due to all the elements of the conductor, we calculate the sum of the magnetic inductions due to all the elements at point P. Consider one such element of the conductor. Let R denote the vector joining the current element to point P. Let theta be the angle between the tangent to the element in the direction of the current, which is actually the direction of vector dl and vector R. The magnetic induction dB at point P due to the element is directly proportional to the current I in the element. Let this be equation 1. The magnetic induction dB is directly proportional to the length dl of the small element of the conductor. Let this be equation 2. The magnetic induction dB is inversely proportional to the square of the distance r between the element and the point. Let this be equation 3. Combining equations 1, 2, and 3, we get dB proportional to I dl by r square. If we express it in vector notation, we get the magnetic induction dB proportional to I dl Let this be equation 4. Since the magnitude of the cross product dl cross r can be written as dl into r sine theta, we can write equation 4 as dB proportional to I dl into r sine theta by r cube. Let this be equation 5. Replacing the proportionality sign with a constant, we get dB is equal to mu naught by 4 pi into I dl into r sine theta by r cube, which can be written as mu naught by 4 pi into I dl into sine theta by r square. In this expression, mu naught is the constant known as permeability of free space, and the value of mu naught in SI units is equal to 4 pi into 10 power minus 7 Tesla meter per ampere. Here, the direction of B will be perpendicular to the plane containing dl and r, and can be obtained by using the right-hand rule. According to the right-hand screw rule, if we place our stretched palm along the direction of DL and we now curl our fingers in the direction of vector R, the thumb of the right hand held perpendicular to the stretched palm gives the direction of the magnetic induction dB at point P. The magnetic induction B is obtained by integral dB in suitable limits. Magnetic induction at point P is B equal to integral dB. Now, let us compare the Biot-Savart law with Coulomb's law. Coulomb's law gives the electric field due to a charge at a distance r from the charge, where the source of the electric field is the charge. The Biot-Savart law gives the magnetic field due to current passing through a conductor, where the source of the magnetic field is the current passing through the conductor. According to Coulomb's law, the electric field due to a charge is inversely proportional to the square of the distance between the charge and point P. On the other hand, according to Biot-Savart law, the magnetic field due to an infinitesimal element of the current-carrying conductor is inversely proportional to the square of the distance between the element of the conductor and point P. According to Coulomb's law, the electric field at point P acts along the displacement vector joining the charge and point P. That is, the electric field acts along the line joining the charge and point P. But, according to Biot-Savart law, the magnetic field at point P acts perpendicular to the plane containing vectors dl and r. The magnetic induction at any point P in the magnetic field of the current-carrying conductor depends on the angle between vectors dl and r, whereas there is no such angular dependence in the case of the electric field strength due to a point charge. However, if point P is in the direction of the length of the conductor, the angle between the current and the line joining the point is 0, and hence the magnetic induction dB for such a point due to the current-carrying conductor is 0. The superposition principle is applicable in both cases. For the electric field produced by a system of charges, the net electric field strength E is equal to the vectorial sum of the electric fields E1, E2, E3, and so on due to the individual charges, say Q1, Q2, Q3, and so on by the superposition principle. If a region has more than one current-carrying conductor, then the net magnetic induction B at any point P in the combined magnetic field of the conductors is equal to the vectorial sum of the magnetic inductions. Say B1, B2, B3, and so on, due to each of the conductors. In fact, the speed of light c in a vacuum is related to the permeability of free space μ0, which is related to the magnetic field and permittivity of free space ε0, which is related to the electric field as c² is equal to 1 by μ0 epsilon naught.